Now, the last thing we discussed here is electrostatic potential energy. I am done with that. Okay, but there are some formula we need to look at here. But before that, in this formula, which show the relationship between electric field and electric potential, you can see negative. I have not talked about it. Though I talked about this. I said the relationship means when there is change in potential, electric potential, with respect to change in distance, we get what we call electric field. But the negative sign here is showing that that change must be decreased. Because I told you that we are bringing the charge from infinity backward, meaning we are reducing the height, the distance of the charge. So reduction in the distance is what call for negative. I need to explain that. So the distance must decrease, but how do we show that the distance is decreasing? And that's the meaning of the word negative. So the negative show that change that I said must not be an increment, but a what? Decrement. That's the symbol. So when I say is the rate of change, we should all know that change can never be what? Increment. It is always what? Increment. Because it will always happen from a high, or it will always move from a high potential to what? A low potential. So movement from a high potential to a low potential shows or indicates the negative in the formula. So let us continue now. Now, electrostatic potential energy. Like I said is the energy a charge acquired by the virtue of the position of the charge at rest. So we can have, I don't want to clean it because we are still going to make use of all this. Okay? So here we can look at formula for electrostatic. So the symbol for electrostatic potential energy is U. And that is, we have the formula to be QV. Charge times potential. Do not forget I've told you that in electrostatic we are talking about what? Charge. And then we are talking about what? Energy. So this one is indicating energy, while this one is indicating what? Charge. So which means there is no how we discuss electrostatic potential energy without talking about the charge, which want to acquire the energy, and the energy acquired by the what? Charge. So mathematically, electrostatic potential energy is given as QV. And we should also recall that V is equals to KQ over what? R. This is one of the formula we know for electric potential as well. Apart from this, yes, V equals to ED. V also equals to. So these are the formula we need to note. Or that this physics is unlike mathematics. Physics, I can decide to generate more than 5 formulae for just one quantity. And that makes you a good teacher in physics. Unlike in mathematics where we have just one formula for area of a circle, one formula for area of a... So just play along the way I've been generating this formula. So note this for relationship between electric field and electric potential. Note this for relationship between electric potential and electric field intensity. This is electric potential, but E stands for electric field what? Intensity. This V also, which is electric potential, can as well be given this formula. K equals to Q, V equals to KQ over what? R. R is the same thing as the distance. Now, there is a way of generating this as well from here, but just to save our time. Now, this K is always very constant. K is always very constant. K is always written as 1 over 4 by E naught. This E naught is called permittivity in science. Permittivity. But in case, if this value is not given, then this entirely, we can be asked to calculate K ourselves. That is when you know E naught. But when you don't know E naught and you need value for K, K is the same thing as 9.0 times 10 raised to power 9 Newton meter square per coulomb square. Newton meter square per coulomb square. Now let me repeat it again. K is called constant. And how do you go for K? This is the formula. But for you to use this formula in getting K, you need E naught, which is called permittivity. But most of the time we need this K, but E naught is not always been given. So we can go for the value of K, which means they have solved this to arrive at this for this. So note this value in the exam may not be given. So K is always 9.0 times 10 raised to power 9, and the unit is what? Newton meter square. Newton meter square then per coulomb square. Meter square. You can rewrite it as Newton meter square per coulomb square. So this line can be written as a negative power. Okay, there's something I want to quickly bring out of this. Let me bring it out. I don't want to clean this one as well. So 1/4 pi E naught, which is equals to 9.0 times 10 raised to power 9 Newton meter square per coulomb square. Okay, now I put R here, or we use D. Now, if I have this, please, I want you to get this very well. If I have this for V, and I have U, let's call this one equation 1, which is the formula for electrostatic potential energy. Q times what? V. Charge times electric what? Potential. Now that I recall, so let's recall that this electric potential can be given this formula ED, can as well be given this formula KQ over what? R. So let's call this one equation 2 now. Now by rewriting this equation 1 using equation 2, I think I'll be having U is equals to Q. Now instead of writing V, now what am I going to write? K Q over what? R. So most of the time you'll be saying that this is the formula for electrostatic potential energy. They will say K Q1 Q2 over R. Please note this formula. This is the formula we use, and this is how we generate it. You may be asked to solve using the formula. You may be asked to show how the formula is being generated. So this is the formula we always use when we are calculating electrostatic potential energy between two charges. This one can be between one charge, while this one is between two charges. Okay? So that is on electrostatic potential energy. So please note all this formula we have on the board, because we are still coming back to use them in solving problems. So note them like that. Note them, and the way I have been generating them, note them. Now let's go to electromotive force. Regardless of the word force, don't forget that I've told you the principle of charge here, like, repair, or like, and track. Now, so let's go to electromotive force. Regardless of the word force there, electromotive force is energy, not a force. Regardless of the force appear in the phrase. So this thing is an energy. So when you hear electromotive force, it is always an energy. And what type of energy is that? Energy that moves charges around the circuits. So on the other hand, we have potential difference. Energy that moves charges between 2 points. So to move charge around the circuits, it is called electromotive force. But to move charge between one point and another point, it is called potential difference. So how do we define this now? Electromotive force is the energy required to move a charge throughout the what? Circuit. It is measured in volts. While potential difference, it is the energy needed to move a charge from one point to another. It is also measured in voltage. We continue in the next class.